Good morning, everyone. Thank you for being here today. I'm going to talk about this new architecture that we designed for real-time video systems to improve the performance. So real-time video systems are used in any setting that we want to send video over a network with low latency to maintain the interactivity of the application. You can think of applications like cloud video gaming or remote surgery or teleoperation of robots and vehicles. And of course, the most prominent application of real-time video systems, video conferencing. And well, when you want to download their app, they show you all these happy faces. But the real experience of using these programs is closer to this, where all those stalls and glitches, they frustrate the users. And when it happens, you might wonder, why is it happening? Is it my ISP? Is it the program? Who's guilty? And I think I have an answer for you. So here, we are sending a video using one of these real-time video systems, WebRTC in Google Chrome. And at the bottom, you can see the network throughput graph. The shaded region is the network capacity, and the line is the amount of data that program actually tries to send. So that the capacity is going to go down and then back up again. Let's see what happens. The video stalled. And it's starting to recover. Let's look at the video again. So the capacity is slowly going down. It stays at 0 for 1 second, and then it goes back up again. But it takes WebRTC a long time to recover from that 1 second outage. And if you look at this part of the graph, you can see that somehow WebRTC realized that something's going on with the network. It tried to send fewer packets, but it responded so slowly that it ended up sending more than the network can handle, and it congested the network, and then it had to spend a long time to recover from that, although the network was actually back. So in a nutshell, we can say that the current systems, they do not react fast enough to the variations in the network. They usually end up congesting the network that causes all those stalls and glitches. So to solve this and problems like that, we designed a new architecture that we call Salsify. It tightly integrates a video-aware transport protocol and a functional video codec that allows the system to respond quickly to the changes in the network conditions, avoiding stalls and glitches. Salsify achieves better delay and better quality at the same time when compared to Skype, FaceTime, Hangouts, and WebRTC with and without a scalable video codec. OK, let's talk about this new architecture. So in general, real-time video systems, they combine two components. The first component is the video codec, responsible for compressing or encoding the video. The second component is the transport protocol, responsible for sending that compressed video over the network, processing acknowledgments, probing the networks, and things like that. And these components, they have their own separate control loops and talking to each other through a very narrow interface. So transport has a sense of the network bandwidth, a bit rate, and it will give that estimate to the video codec. Video codec, in its own internal control loop, starts to produce compressed frames targeting that bit rate. And now transport has little control over what video codec does. If video codec has overshot that bitrate estimate, the transport still has to send that data, although it means that the network might get congested. And the actual problem is that that bitrate is only achieved on average. So the codec might create a frame that is too big, and it tries to compensate by making the next ones smaller, but that big frame can still congest the network. And because of this fact that the bitrate can only be achieved on average, it doesn't make sense for the transport to update that bitrate estimate too often. So we ended up with a system that is slow to react to changes in the network. In Salsify, we decided to explore a more tightly integrated design, where the transport protocol and the video codec, they run in lockstep, and there is only one unified control loop that governs the whole system. But before I talk more about this architecture, I have to say that the individual components of Salsify, they are not exactly new. So the transport protocol in Salsify is inspired by Sprout and Packet Pair. The video format VP8 was finalized 10 years ago. And the functional video codec that we used in Salsify, I talked about it at NSTI last year. What's new here is the architecture, the way that we put these components together, creating a system that can respond quickly to the changes in the network. OK, I'm going to start by talking about the transport protocol in Salsify. So the goal of the transport protocol in this system is to make sure that no individual frame is going to congest the network. So there is no notion of average bit rate here. It only answers to one question. What should be the size of the next frame that doesn't congest the network? No bit rate, just the next frame size. And to answer this question, transport uses packet interarrival time reported by the receiver. But there is one catch. The receiver is not transmitting frames continuously. So the way that the system works is that the video codec gets a frame from the camera. It spends like 20 milliseconds, 40 milliseconds compressing that frame. And now when the compressed frame is ready, transport will send that over the network. Then we have to again wait for 40 milliseconds for the next frame to be ready. And the receiver, if we use like a naive version of packet pair or a sprout, it might see all those pauses as a sign of congestion in the network. But that's not the case. The sender just didn't send anything. So Salsify's video-aware transport protocol is aware of that behavior, and it treats each frame as a separate packet train to improve the estimation of the network. OK, now in Salsify, we have a transport protocol that tells us about the size of the next frame. But there is a problem at the codec side. So for any codec, it's challenging to come up with the right quality settings up front to meet a certain target size. They tend to overshoot or undershoot their targets. And that's actually the reason that the video codecs, they achieve the bit rate on average. But they can't do that very well for a single frame. One solution to this problem can be trial and error. Imagine that you want to buy shoes online, but you're not sure about the size. What you can do is that you can actually order multiple sizes, try them on, and just pick the one that fits the best, and just return the others. One solution here now can be, what if we encode a single frame with different qualities? And after we learn the frame sizes, we just pick the one that fits the network the best. It sounds good, but unfortunately, it's not possible with the existing codecs. I'm going to tell you why in just a minute. So the thing is that the encoder, the program responsible for compressing the video, is stateful. After it encodes the frame, it goes through a state transition that is impossible to undo. It's like you can imagine that in that shoe example, you put on the shoe, but you can never take it off again. So it doesn't matter if you have ordered 20 sizes. As soon as you try on the first one, you have to commit that forever. So when the encoder encodes the frame, it goes through this state transition, and you have to commit to that frame. That frame is now a part of the video stream. You got to send it over the network. It has to be received on the receiver side, and the future frames are going to be dependent on that. And if you look at the interface that the current video codecs gives us, you can see that the encoder is a program that just consumes images and produces compressed frames. The state is completely internal to this encode function. There is no way to save that. There is no way to restore that. And if there was a way to save and restore this state, we could have just saved the state before trying one quality setting. And if the size is not the desired size, we just throw it away, go back to the old state, and encode a new one. But Salsify's video codec is implemented in explicit state passing style. It means that the state object is explicit in this interface. You can save it, you can restore it, and we can encode based on your state. If you don't like the output size, if it's like too big for you, you can throw it away. You can go back to the beginning state, encode a new one. And using this functional video codec, Salsify can actually explore different execution paths without committing to them. So what the codec does here is that it provides transport with three options. The first option is a version with a slightly higher quality than the previous frame. The second option is a frame with a slightly lower quality than the previous frame. And there is a third option that wasn't available in conventional video codecs. The transport can actually discard the frame. So if the transport realizes that this frame, I can't send anything right now, or the network is congested, it has this option to discard the frame. But in the traditional case, if we encode a frame, we are committed to that. We have to send that frame over the network, although it might congest the network. OK, now we have a transport protocol that tells us about the next frame size that the network can handle. We have a video codec that gives transport options, and the transport can pick the one that fits the situation better. And now there is a unified control loop that brings these components together. So for each frame, the codec will give us two options. One version with a slightly better quality, one version with a slightly worse quality. And transport has an estimate for the next frame size that the network can handle without causing delays or excessive queuing. And the transport looks at the output sizes and picks the one that doesn't go over that estimate. It picks the option, tells the codec that, OK, I picked this one. And the codec will base the next frame on that exiting state. Again, it gives transport two options. The transport will probably update its target frame size estimate based on the latest feedback. And again, picks another option, tells the decoder that I picked this one. And the decoder repeats this. And sometimes, like in this situation, you can see that the transport thinks that the network can't handle more than 5 kilobytes. But the frames are 70 kilobytes and 50 kilobytes. So transport just tells the codec, sorry, just discard all of them. I'm not going to send anything at all. And the codec says that it's completely OK. I'm going to encode the next frame, the latest frame from the camera, and I'm going to base them on the previous state. Don't worry about it. And this continues, and we keep sending each frame. And as you can see here, each frame actually becomes a switching opportunity. If transport realizes that the network is congested, it can just kill the encoding process at exactly that point, keeping the program from causing more packet loss. And as you can see, there is no notion of bit rate, and there is no notion of frame rate in this system. Frames are only encoded and sent when the network can actually accommodate them. OK, so these are the highlights in Salsify's new architecture. So to compare Salsify with other systems like Skype and FaceTime and the other real-time video systems, we built a measurement testbed that has three important characteristics. First of all, it has reproducible input video, reproducible network traces, and it can run the unmodified version of system under test. Either it's Skype, either it's WebRTC, or Salsify. We can run them as black boxes. We can run the sender and receiver as black boxes. No change to their code is necessary. And the target quality metrics for target QoE metrics for this measurement testbed are per frame quality and per frame delay. We talked about the details of this system in our paper, but just to give you an idea about how this system works is that this system has a barcoded input video, which means that every frame has a unique barcode. And we use that barcode to actually trace the frame from the sender to the receiver. So we match up the frames at the sender side and at the receiver side using these barcodes. And based on the timestamps that we have for the sent image and the received image, we can see how long did it take for the frame to get from the sender to the receiver, and also what was the change in the quality. So using this measurement testbed, we compared Salsify with 5 other schemes: Skype, FaceTime, Hangouts, WebRTC with and without scalable video codecs. And here you can see video quality versus video delay. The x-axis is video quality. It's flipped, so better is up and to the right. we wanted to actually see how these ideas in Salsify are contributing to the final performance of the system. So we started with building a basic real-time video system with a conventional transport and a conventional video codec, like in the conventional systems. And the dot ended up there. It is slightly worse than WebRTC and Skype, maybe because like the encoder was written by one person in 3 months or something like that. But we got somewhere close to like those systems. Now we took out the transport, the conventional transport, and replaced it with this new transport that tries to take the control of video on a per frame basis. The codec is still a conventional codec. It's still a codec that has to come up with the quality settings up front. It can't do that trial and error that we talked about. And the dot moved there. So the delay got much better, but the quality is slightly worse. And now, if we throw everything that we have, this functional video codec, this video over transport protocol, this unified control loop at the problem, the dot will go up there with better quality and better delay than any of the other systems. These are the results on Verizon LTE trace. You can see the results on AT&T LTE trace. And these are the results on T-Mobile UMTS trace. And also, we wanted to see how would Salsify work on a network with no variability, a network that is not variable. And these are the results on an emulated Wi-Fi that the network capacity is fixed, but it only has occasional packet loss. OK, remember this video at the beginning of the talk? On the left side, you can see Salsify. On the right side, you can see WebRTC. And let's just see how Salsify would react in the same situation. Stalled, Salsify comes back. And now WebRTC. So you see, the network was out for a second, and Salsify was out for a second. It quickly recovered because it didn't try to congest the network when the network was actually out. And as you can see, it gracefully tries to match the network capacity. The second example is we are going to have multiple network outages, and each is going to be 1 second. Left side against Salsify, right side WebRTC. Network's out, Salsify recovered. So by reacting quickly to these changes in the network, like the losses, outages, or drop in the capacity, Salsify can actually avoid congesting the network, and it can react more quickly to the changing network conditions and can recover more quickly. OK. First of all, I have to say that codecs, they have been treated as black boxes for a long time in video systems. Last year at NSCI, we talked about a project called XCamera, where we decided to actually break this black box, define a new interface for the video codec, and we used this functional video codec to do massively parallel video compression on AWS Lambda. Today, I talked about a system that used the same abstraction for the video codec in a completely different sizes to compress frames to the right size at the right time. You see the same interface, two completely different benefits. So we can just think that there might be a lot of other applications that can actually benefit from this richer interface to the codec. And we encourage the codec designers and implementers to include this save and restore state in the codecs. Even if it's large, even if it's opaque, there are a lot of applications can actually use that. And a more important point, it seems that at least in this context, the improvements to video codecs have reached the point of diminishing returns. But if we decide to change the architecture of these video systems, they still can yield significant benefits, like we saw today. So Salsify is a new architecture for real-time video systems. It tightly integrates a video over transport protocol with a functional video codec, allowing the system to respond quickly to the changes in a network. It achieves 4x better delay and 2 dB higher visual quality when compared with Skype, FaceTime, Hangouts, and WebRTC with and without a scalable video codecs. Thank you so much.
Thank you. Very, very interesting talk. Very nice talk. I just have one question, one comment. A comment is on the mobile terminals, the video codec often is in ASIC, is hardware. The bar to changes is really high. That's a comment. Number two, since your technique is actually require the codec to produce like 2 versions at the same time, that obviously increase the computation overhead. I wonder, do you have any comment about the this overhead there? Thank you.
Thank you very much for your question. We totally agree with you. I mean that unless we can actually implement this codec in hardware, it's not really possible to use Salsify on like mobile devices. And I think our goal here is to actually encourage the codec developers to include this interface in the next generation of video codecs. So that's completely true. Unfortunately, we only have this interface currently in software, and I don't think there is any problem with implementing that in hardware. The only problem is probably just convincing all these vendors to include that interface in their system. And about the second question, yes, we have to encode 2 versions for a single frame, and there is a computation overhead. But even like the software codecs on a single core, I guess they are able to produce like 60, 70 frames per second at 720p. So we can still achieve like high frame rates using software, but you're right, there is like 2x more compute. Thank you.
Sanjay from Purdue. This is a very cool direction that I think this work opens. So I'm not a video coding person, but there's something I didn't follow. So typically you have temporal dependencies in video coding. You have an iframe and p frames, right? So if you do transmit your iframe already to the client, is there a way for you to dynamically switch to a p frame of a different quality? Or can you only switch frames at the next iframe or something like that?
Thank you for your question. One point here is that, first of all, keyframes, or in another saying the iframes, they are actually more expensive than p frames. So basically, when you ever decide to actually send an iframe, when you decide to actually restart the stream, because a keyframe or an iframe, it doesn't have any sort of dependencies on any other frames. It's completely standalone. And because of that, they are huge. So there is like a penalty to actually sending keyframes. But about the quality, you can actually change the quality on a per frame basis. The problem that we are seeing here is that you decide on some quality level and you encode the frame, but you see that, oh, it's too big, I can't send this. And there is no way to undo that. But if you ever decide to like send an iframe, you can always do that. It's just expensive.
Okay, I'll take it offline.
Okay,
thank you.
Thank you.
Hi, very nice work. David Chu at Google. So the question I had was with regards to your evaluation results. What you showed was on, I believe, LTE networks, you were Pareto optimal. Salsify was Pareto optimal. But on the Wi-Fi network, you were Pareto optimal along with other options. Could you comment on why Salsify maybe is not doing as or dominating all other options in the Wi-Fi case?
That's a very good question. Let me see. Actually, I think I have a backup slide for that. The thing is that the variations in these LTE networks are really huge. So this is like a, I think, 3-minute trace from AT&T LTE network, and you see all these variations. The network capacity goes up to like 10 megabits per second, and it goes down to like 100 kilobits per second. And because of all these variations, then the other schemes like WebRTC or Skype, they can't respond to these changes very quickly. But when the network conditions are okay, like in our emulated Wi-Fi trace, we have a network with a constant capacity. So the capacity of the network doesn't change. And we often see that in those situations, there is not that much of a difference between the schemes. Because when the network conditions are OK, you can just find some safe bit rate and just keep transmitting at that. There are no actual challenges. And the design of Salsify is focused towards variable networks. Thank you.
Victor Vasilyev, Google. So I have the question. So if you look at that graph where you compared WebRTC and Salsify, you can see that there is a bandwidth dip where bandwidth goes to 0 and recovers, and Salsify picks up on that recovery almost immediately. Like if you look at this and...
Are you talking about this example?
Yes, this one. Yeah. Like if you look at what happens, like, so it goes down and then it goes up pretty instantly. So one question I have is, so how much of the improvement you've observed is just related purely to having better bandwidth estimation, and how much of it is actually due to integrating application layer with video codec?
Thank you so much for your question. So I think if you look back at these results, we can see that we replaced the conventional transport with a version that basically estimates the network better. It's aware of the video's behavior and things like that. And well, the delay got much better. But as you can see, the quality is still worse. So I think that like different components in Salsify, this tightly integration, the video over transport protocol, they are actually important to the final performance of the system. So like in one example, we made the transport protocol. Excuse me. So for example, here, if we use like a naive version of packet pair or sprout, where it doesn't know that the sender actually pauses between frames, this is where the dot will actually end up. The functional video codec, the transport, everything's good, but the only thing that we took away is that knowledge that the sender is not transmitting continuously. And the dot will end up there with like a very low quality, of course very good delay, but a very low quality. So to answer your question, I think all these components are kind of important. If you take one of them away, it may still affect the performance of the total system.
All right, I'm going to wrap this up right there because we're running a little late, so maybe do that offline. But thank you all, and thanks, Ajay, for the talk.
Thank you so much.